Now, in this video, we're going to look at how we can calculate probabilities from a two-way table. Now, if you have raw data and you need to first make the two-way table, then you'll want to look at a video. I've made one myself for how to use the pivot tables in Excel in order to create your two-way table. But in this particular example, we're going to start from the idea that we already have our two-way table, and then we're going to calculate probabilities. Now, there's nothing in particular about this example that requires you to have Excel, since we already have the two-way table created. But it certainly will allow us to represent our values that we calculate as either decimals, percentages, or percentage or fractions very easily. All right, so here's our data, and this is data that is on students in school and their favorite sports, baseball, basketball, or soccer, and their favorite subject in school, math, history, or art. And so what we're going to do is we're going to calculate some probabilities based on this raw data, including some conditional probabilities, and just use our probability rules in general. And then we're going to ask a question at the end about whether or not this data is independent. All right, so what is the probability that someone randomly drawn from this data set likes soccer? Now, it's important to think about this data as we're doing descriptive probabilities, essentially, descriptive proportions. If we want to infer information, then we would need things like chi-squared tests and things like that, more advanced statistics. So here we're just using the raw data and saying, based on this data alone, what are our conclusions about if we were to randomly draw someone from this particular sample? So what is the probability that they like soccer? Well, if they like soccer, we're simply going to take the number of people who like soccer, which is 154, and then we're going to divide it by the total. And so 154 divided by the total. Now, the default display in Excel is as a decimal. But of course, on the home screen, you can change this to a percent if you want. Or if you go into the number properties, you can actually have it display as a fraction. Now, one danger of doing this is that the default settings for the fraction number are not, they're not good because they're basically, they assume that you're going to go to one value in the denominator. But if you go to fraction and you select up to 3 digits, you can actually get this to display as a reduced fraction version of the numbers we have in our table. What about if they like art? Well, if they like art, then again, we're going to look for the total number of art people, and we're going to divide that by the total. And then I'm going to display this as a percentage. Keep 2 decimal places. And then now what if they like art and soccer? Now, if they like both of them at the same time, and then we need to look at the intersection of where art and soccer occur. And so that's going to be, here's art, here's soccer. It's going to be these 69 people. We're still looking at the total proportion in the data set. So we're still using the grand total, the total of all the totals. Now, what if they like art or soccer? Now, to do art or soccer, you need a formula. You may recall that the or condition is the probability of A or B is equal to the probability of A plus the probability of B minus the probability of A and B. Now, one danger that sometimes comes up in these table examples is that students will interpret A and B as a multiplication. There is a formula that if A and B are independent, then yes, you can multiply them together in order to get the probability. But we do not know that this data is independent. And so we can't use that multiplication rule in order to do that calculation. We couldn't use it to do the calculation here either. But we have the calculation from the table. And so as long as we use the values from the table, then we're okay. So if we use this calculation, we've actually already calculated those values. We just take the probability that they like soccer plus the probability they like art, and then subtract off the probability that they like both at the same time. Why do we do the subtraction? Because the people that like soccer and the people that like art are in both of those. And so we've counted those people twice. We want to remove that one copy of them so that they're only represented one time. Now, the formatting on what comes out when you have multiple formats, in this case, it converted everything to a percentage with way more decimal places than we really need. So if everything is already decimals, then it will obviously appear as a decimal. If you've already converted everything that you're inputting into a fraction, then it will, as a display, then it will convert to a fraction also. But when it's mixed, then it will default to something. In this case, it converted to a percent. All right, so those are the sort of basic probability rules. We could insert here, I suppose, the complement rule. What is the probability that someone doesn't like soccer? That's certainly a possibility. If they don't like soccer, then you're simply going to do the complement of liking soccer. So 1 minus. So one minus the probability that they do like soccer. And again, notice it copied that formatting over. So you don't have to like count up all the people in the table that don't like soccer. What about they like soccer given that they like art? Okay, now the given is that clue in the statement that this is now a conditional probability. And when we go to conditional probabilities, we can no longer use the 416, the grand total, as our denominator. We have to change the denominator to just include what is given. So let's look back at our table. Like soccer, given that they like art. So given that they like art, we're starting just in the art category. And then we want to know how many of those people like soccer. So we're going to use the numerator to be that intersection again of soccer and art. But what goes in the denominator is not the grand total, because we're only talking about people that like art. So what's going to go in the grand total in the denominator is the total number of people that like art. So this is going to be 69 divided by the given category, the total for the given category, which is 140. And if we do the reverse, the numerator is going to be the same, given that who likes art, given that they like soccer, that's still art and soccer together. So the numerator is the same, but now we're going to be saying that given that they like soccer, we're only considering this column of people who like soccer. So the denominator will be different. The denominator will be the number of people who like soccer. So 69 divided by 154. Now, the hard question then is, are these two variables of sports and favorite subject in school, are they independent or are they dependent in this data set? Not inferentially, but just descriptively in this collection of information. Now, the way that we test that, there's two ways that we can test that. So if two variables are independent, then the probability of A is equal to the probability of A given B, or the probability of A and B is equal to the probability of A times the probability of B. We can test either or both of these. Now, one caveat that it's worth pointing out here is that if you get one case where it's not independent, where these don't equal, then you can say, okay, they're not independent. But if you do get a case where they do seem to satisfy this condition, then there are more cases you have to check. You have to actually check not literally every possible combination, but enough that with the complement rule in mind, that you've checked all the possible combinations, ruling out that complement rule. We're not going to do that here. That's somewhat too complex for this example, but we're going to test one example. It's very unlikely that randomly selected data is ever going to be descriptively truly independent. It can happen, but it's really only when you sort of manufacture it that way. Now, the way that I've set up these questions, I've set them up particularly to test this first condition, the probability of A versus the probability that A given B. So we can just look at our table. So let's look at the probability of A. So let's say the probability of art, since that's easy to convert back and forth in our head to a decimal. The probability of art. Okay, well, that's 33.65%. What about the probability of art given soccer? Well, that is definitely not 33%. So that already tells us that these variables are not independent, because if they were independent, these two probabilities would be identical to each other. Now, we could also do this calculation. We could calculate these two probabilities, the probability that you like soccer and the probability that you like art. Probability of this times the probability of that. And again, that's a percentage with way more decimal places than we really need. And we would want to compare that to the probability of soccer and art, that intersection. And again, just to put them in the same format, 16% and 12% are not the same value. So we know this is not true. Again, this is why we can't use this multiplication rule to do this and condition in our OR formula. We will get the wrong answer because they are not independent. We can't make that assumption without checking it. And here we've seen that, in fact, it's not true. So the answer to this question is no, they are not independent. Again, if they had been independent in this one calculation, we would have more things to check. But once we're clear that there's at least one case where they're not independent, then we can say generally that they're not independent.